Okay, great. Thank you very much for inviting me to speak at your AGM. And I really, really wish I was there in person meeting you all and having all those side conversations, which is what a news network needs to do. But we'll do our best with what we've got. So I'm here to tell you essentially why CCP QC exists in terms of quantum computing. We were successful in getting funding, but we're not quite the same as the other CCPs in what we're aiming to do, as you'll see. But I'm going to start by putting stuff in context in terms of what we do with computing. As a computational physicist myself, the goal, we're always looking for more computing power so we can do better simulations. And our current computers are already very powerful, but we've hit the buffers in some ways on the conventional computing. We're at the limit of what we can do with silicon chip technology. And the other side of this is that the energy consumption from all of the big data centers and high performance computing is far from optimal, and it's a significant contribution to resources and global warming. There is lots of room to improve on energy consumption, and that's not what we're about, but I just thought I'd put that out there as another factor in wanting to find other routes to more powerful computing. So what happened with silicon chips? Well, here's a whole bunch of the history of the timeline for CCP5 in this 40 years laid out in terms of what the processing power was for Intel's chips. This line up to about here is the famous Moore's law. That's an earlier version up to 2000. It's got the chip names on, but and it came from their website. I plotted this one from data that I found on their Intel's website, their historical data, because they don't talk about exponential growth anymore. Somewhere in the early 2000s, late mid 2000s here, what happened is they stopped getting faster. So this blue line here is the speed in hertz on the scale here. And it's kind of not as good an exponential growth as the number of transistors, which is what the black line is, the original one. But then it's leveled off here. Now, what the red line is the feature size. So they've been etching smaller and smaller features on the chip so that they can pack more sort of transistors and gates into a smaller volume. And that's kept going down, but the speed has not gone up. And so what you find here, and I stopped trying to plot, instead what you've got are a lot more chips. So you can get a chip that's optimized for anything. Mobile phone, for a toaster, for extra robust if you want to put it in extreme environments, smartphone versus not so smartphone. Intel have a chip for it, but they don't have faster chips than this anymore. And what they've hit is a physics limit. You can't cool the silicon chips any faster. Heat conduction is a basic property. And so we've hit the top speed for this design or this method of doing silicon chips. And instead they're diversifying. So we've got sort of co-processors for all sorts of different things. You've got multiple cores on one chip. You've got all sorts of optimization going on. So where is that leading next, though? Because there's not more that we can do with this silicon technology. And there have been all sorts of lines of work. This is really science now that I'm putting up, looking at other ways to compute. So there's the quantum one. That's a picture of a 16-qubit IBM chip. People have been interfacing neurons and silicon, and they've been building neuromorphic chips to do very different models of computing. That's chemical reactions, using slime molds to compute. Reservoir computers, basically you've got, this is graphene in a resin substrate with a whole lot of electrodes in it. And depending on what signals you put in, you get a different set out. So it's done some signal processing for you. And whether that can compute or not, it's still science, but there's some really nice work on that, for example. And lots has been talked about DNA computing, and this is just 6 examples that I picked. So we're diversifying not just the chips that Intel are making and others, but we're also diversifying what kind of devices and what models of computing we might be able to use. But now, how do you use something like that? You're going to need to co-design both the algorithms and the hardware, and you're going to need to have some goals in mind for what it is you want to try and apply these to. So this is a bit more that's looking at this in kind of words and categories. So what we have in practice is co-processors, right? We've had graphics cards for decades. So it offloads certain tasks to processing devices that are optimized for that task. So real-time drawing of your screen, for example, at the speed you need to, as a human, to take in the information on it. FPGAs have taken over more from ASICs, but if you've got a particular configuration, then you might just make that it's worth making multiple of them, then you might end up with one of these for a particular application. And now if you look at those unconventional ones, none of them do anything without being hooked up to a conventional computer. So they're also hybrid. You've got controls, you've got inputs, outputs. So the simplest way to think of what you're doing when you looking at a more unconventional computational device is to think of it as a coprocessor. So in practice, hybrid computational systems are the norm. It's what we're used to. But the theory is single paradigm. We have classical computing as Turing machines, which doesn't look like anything anybody builds. Analog computing has Shannon's general purpose analog computer theory to it. Quantum has several different models. I'll come to this more about this later. But each model is framed as, is it a universal quantum computer? It's not framed as, would this be a good thing to hook up to ordinary HPC to do a specialist task? Linear optics is not quite quantum computing. That's a kind of fun story that I won't go into here. But there are other models that are, if you like, partly quantum in how they, and that they're more powerful than classical, but not universal. So given that there's all of this diversity coming along, we better make sure we're clear what it is we are doing with all of our computation. So this is an old figure that I drew a long time ago when I realized that a bunch of my colleagues in physics didn't actually know where computation fitted in. They either were doing experiments or doing analytical calculations, and they weren't clear what the role of the computational component was. So I drew this little simplified model of it. And the first thing, of course, is we simulated models. We don't simulate physical systems. We simulate our model of the physical systems. And conflating that causes a lot of confusion among people who are not computational. And the people that do analytical work kind of think of this as the main route. And that would be nice if we had tractable mathematical models, but mostly we don't, particularly for more complex systems. And so we're nearly always needing to go this route to understand what it is our model means and whether it's a good model of the physical system that we want to understand. It also helps to have a good picture of what actually using a computer is. So this is a slide from my public outreach talk. It's the pretty version, but there's also this is the journal article, very, very readable, very interdisciplinary. So I'm just going to give the one slide here to show how you can think about what's happening when you are actually doing a computation. Because we need to make sure that what we're doing is actually computing and not doing a scientific experiment or engineering something or some other human activity. In here you can see how all these all interlink. What you can draw a similar diagram for science, for engineering, and see where the sort of change points are and how they relate to each other. But what I want to look at here is to think what we do when we're computing. We have something, we have a problem that we want to solve. Our mathematical models that aren't tractable, for example. If we want to compute with them, we're going to have to encode them into a physical model, our model of the physical computer, in such a way that we've got a faithful representation of them, so that what we're going to do with the computer is actually going to calculate what we want. So there's an encoding step here. Then we actually put this into our physical computer, press go, our program runs, whatever else it does, we get some output, and then we're reversing this process. And then we have to take the output in the computer language and decode it back so that it corresponds to the problem, and see what it says about the solution we get. So you can see this as a nice little flow here. And now here's quantum computing. I've just flattened out that diagram so we can see that we have our input, which is our problem, not necessarily quantum, but it might be. We're going to need to encode it into a quantum state of our quantum computer now. We're going to do some quantum style processing on it. We'll get a new quantum state, which we'll need to measure to get some output. Then we can decode it, and our potentially quite different problem will give us our result. So I've put U for unitary evolution because that's the basic way that quantum mechanics works, but you could have it as an open system, and I couldn't just enlarge that. So this is not meant to be excluding open system. It's I could just add the environment into the state here and make it all unitary if I wanted to. So what's this going to look like, this U here? It could be a sequence of gates, much as you would think of low-level classical computing, where you might do a C0 gate or a rotation or something. Or we could engineer a Hamiltonian such that our output state is the time-ordered. This is just running our Hamiltonian, which is in general time-dependent, for a length of time applied to the input state, and that will give us our output state. So this model covers most of quantum information processing, in fact. Includes communications where we're aiming to get the input and the output to agree, but we've sent it through some sort of noisy channel, or and it may not be so easy to ensure that the message isn't garbled on receipt. One thing to note, which characterizes computation, this encoding step generally has some arbitrary choice in it. So if we want to use spin up and spin down to represent 0 and 1, it doesn't really matter which way we do it. spin down can be 0, or spin up can be 0, so long as we're consistent throughout our encode and decode step. But that's one way to recognize when you're really computing something, is that there's this encode step is non-trivial. So this is my one slide on why should we be especially interested in quantum computing as one of our routes to get more computing power. Basically, the idea is that quantum logic is different from classical logic, and it allows greater efficiency for some computations. So we've got, classically, we've got bits, we've got binary decisions, and we've got random numbers can put in there. In quantum, we can have these superpositions where alpha and beta are complex phases. So we don't have to be 0 or 1. And so we can be in a superposition as well as having binary decisions. And we get random numbers for free, essentially, as out of our measurement outcomes, whereas generating a good source of random numbers classically can be hard work. So we get different computation. The question is, how different is it? So computability is the science of what can be computed and what is incomputable. And complexity is how efficiently it can be computed. This is all very much theoretical computer science level. And to the best of our current knowledge, quantum computability is the same as classical. So it's not that we can compute things that we couldn't because it was impossible classically, but we can compute things maybe that are faster, and therefore we couldn't classically because we didn't have enough computing power. Because there are cases, provable cases, where the complexity differs. So some problems can be computed more efficiently. So encoding matters because it determines what physical resources you need to actually build your quantum computer. There's actually nothing quantum about this, but it got drawn out. We got so used to classical computers are binary that people stopped thinking about why. Why did classical computers take over from analog computers? And the reason is that analog computers encoded this way, unary, and binary encoding means you need less. So there you need n, and there you need log n. So you need less resources. You get an exponential reduction in the memory you need. Floating point numbers are even more efficient. There you're trading precision for memory. So this is, again, just a pointer that that this matters. And again, I've hit this quite often in talking to people who are not used to thinking about computation and not realizing that trying to build a quantum computer that works like this may not be a useful thing to do. So what sort of quantum computers are out there? Well, certainly if we look at the models, we haven't fixed on one at this point. We still have, even if we just look at binary and data encoding, and binary, so discrete gate processing, because we're just applying gates. So really the quantum equivalent of a classical computer would be the circuit model. But we also have a model called measurement-based or cluster state quantum computing, and they're not as, there are some greater efficiencies you can get out of this, trading time and space resources, for example. There's analog versions. These are the equivalent of analog computing in quantum. And then you can do something that you don't really have a classical equivalent of, which is encode the data into in binary, in bits, but then do that continuous time processing using a Hamiltonian. And in a sense, because I want to sort of push open thinking about what computation is, it illustrates nicely what the difference between classical and quantum computing is. So bits are either 0 or 1, and you can flip between the two values, but qubits can be in a superposition, and they can change smoothly from 0 to 1 or anything in between. So it makes sense that we have discrete gates for bits, because bit flip is essentially all you can do to one bit. But for qubits, exact bit flip is just as hard as any other rotation. You do a bit flip and you might under or over rotate, and you have to deal with that with error correction in a way that just doesn't apply in the classical case. So it makes sense to do continuous time evolution for qubits in a way that it doesn't for classical in that model. But there are other classical models like spiking neurons, for example, where you do have continuous changes. So quantum scale engineering is hard. We've reached the scale on chip feature size that we need to, we're going to take quantum effects into account, but it's hard. So where do we gain when we try and do quantum computing? So one thing we can do is put an input in that is a superposition of all the possible inputs. And then we can run the computation on that, all of them at once. So it's like parallel processing, but instead of needing 8 processors here, you get to do it on one. Of course, there's no free lunch. What you get is a superposition of all 8 answers. And then you need a programming trick to select the answer that you're interested in. And so the realization that quantum algorithms could be really interesting was people finding the first few of the tricks that started with something like this and then extracted the answer they wanted with an efficient set of quantum gates or quantum program. So if you can do that, if you can find your algorithm, you get a quantum advantage out of it. So building quantum computers, there are many models, as I've just illustrated. There are also many choices for what to build them out of. And people are working on atoms, ions, photons in various different wavelengths, electrons, flux, so superconducting circuits, defects in crystals, nuclei using MRI type operations. I'll skip how the light works, but and go to who is building them. So there are universities and research centers developing hardware and software, but it's also become very hyped in, with companies. So here's a 7-qubit IBM chip, and I've put that picture in partly because I want you to see that at the moment, for a chip like this, you can see the individual qubits with the naked eye. That thing is like, you know, a few centimeters either on each side. And these little zigzag things are microwave resonators because the energy levels in here are at the microwave level. And microwaves are bigger than the chip, so you have to fold up the resonators. It also means they have to run at microkelvin temperatures because they need to be below KT for microwaves. So there's a lot of kit involved in running even a small chip. So how many have we got currently? So IBM and Google are playing at around 65 qubits currently, I think. So instead of 7, they're packing a lot more on, or maybe 2 chips like that. The ions, maybe 100 in a string. I don't know the exact architecture they're developing here, but I do know that the university research group that's a spin out from. PsiQuantum do photons, and they're keeping their cards very close. I don't know what stage they're at. D-Wave have a couple of thousand, much smaller qubits than this, but they're very noisy because they're not quite as powerful as a consequence. they're also not designed to be quite the same type of processing. They're designed for that continuous time processing for optimization problems. So essentially, that is why these ones are so big, because they're less sensitive to the atomic scale noise if they're that big. When you make them smaller, you have to deal with how to get the noise levels down, and that's hard engineering. I'll skip through looking at time here. This is the first time I've given a talk like this, so I didn't get the timing quite right on the number of slides. So Shor's algorithm, if you've heard about it, about factoring, sounded like it was the thing we're building a quantum computer for, but actually not, because it'll be a long time before we have enough qubits to break the RSA that we can do classically. However, if we want to simulate a quantum system, 50 or 100 qubits is going to be enough to do something that we can't do classically. And of course, you can simulate larger quantum systems, but only at the expense of being restricted to a subspace of Hilbert space that is about the size of less than 50 qubits. So CCP-QC, our aim is to work with other CCPs and the quantum computing community to help develop the first applications for the scientific computing that the CCPs do, which means we need hardware that's going to be co-processors, because you're only going to be putting quantum computers in where you've got your real bottlenecks on the classical processing. So as you'd expect, that will look like a familiar set of activities for a CCP that you're well familiar with. The main problem has been that we went into lockdown before we'd even had a launch meeting. So we're trying to get a new network off the ground and get to know all of the other CCPs with only online meetings available pretty much. And I'll just finish with the UK quantum computing landscape so you can get a feel for what's coming. The investments have started around 2014 with a quantum computing hub. The hubs were renewed in 2019, and there's a lot of innovation funding gone to get companies and spin-outs pulled in too, and a national quantum computing center, which has to start with about 80 million, but there will be more. And this is one place we might expect testbed hardware to appear that we can start to try new quantum classical algorithms on for scientific computing. In the global context, you'll have noticed my list was very US based. Rigetti have just been part of a partnership with innovation funding to build a quantum computer of their type in the UK. So we'll see where that sits in the mix of things that are available. The National Quantum Computing Center is only just getting up and running. They've got a building to build. So yeah, at the rate that we're ready to use stuff, it'll take a while to develop the first test applications. Hopefully we'll also have the hardware coming along at about the same rate. So I'll stop there. I'll go back to that. The website is developing too, and take questions if we've got any time.